Hello, everyone. Welcome to our webinar. In today's session, I'll be introducing RocSlope, the latest addition to the Rocscience suite of softwares. RocSlope is used for 3D block stability risk assessment of rock slopes. My name is Angela, and for the past 4 years, I've been involved in managing and developing the rock engineering programs at Rocscience. You may be familiar with some of them. They include DIPS, S-Wedge, rock plane, rock topple, unwedge, rock support, C-pillar, and now RocSlope. Today, I am thrilled to be showcasing RocSlope. This is something that my team and I have been working very hard on for the past year or so. So big shout out to my team for this accomplishment. I also have here with me Dr. Alireza Azami, who will be the moderator for this webinar. And please, if you have any questions, feel free to type them out in the chat. I will try to stop periodically to answer a couple of questions as they come in. And now for a quick intro video. Let me pull that up. Moving on. In this webinar, I'll be going over the following: modeling 3D block stability and structurally controlled slope failures in RocSlope, particularly how we define the slope geometry, material regions, groundwater, and most importantly, the geological structures. Then interpreting the results of the limit equilibrium analysis to identify failure locations and magnitudes. In the case of a deterministic analysis, we can obtain factors of safety, and in the case of a probabilistic analysis, probabilities of failure. I will also talk about key block analysis and the visualization of critical parameters in a heat map applied over the slope. And finally, dealing with uncertainty of material and joint strength properties with a probabilistic analysis. In general, I'll be providing an overview of the main features of RocSlope and its applications. And at the end, I'll be doing a live demo of RocSlope, as there's nothing really better than seeing it in action. Now, our vision behind RocSlope is to ultimately bridge a gap between existing tools and what the industry has been asking for. And that is to provide a software that can handle true 3D slope geometries, whether that applies at the bench, interramp, or pit scale. In civil applications, that might include man-made slope cuts and natural slopes. We want the program to be comprehensive, packed with features that extend beyond the modeling of a single block on a dry slope. RocSlope offers a wide range of capabilities to handle complex models, including the ability to define different shear strength criteria, multiple materials, groundwater conditions, and various loading and support configurations. Most importantly, RocSlope is a software specialized for modeling structurally controlled slope failures. With that in mind, we designed the model inputs, results visualization, and overall workflow catered exactly for this type of analysis. And like all Rocscience softwares, we want the tool to be easy to use. RocSlope offers a familiar and intuitive UI comparable to that of Slide 3 and RS3. We also offer integration with other Rocscience softwares like DIPS, Slide 3, and RS3, so you can leverage your existing data and models. Typical model creation time should be a matter of minutes. And a typical model like the one you see here of the open pit would take about a couple of minutes to compute. So what is RocSlope? As the name suggests, it deals with rock slope stability, specifically failures which are structurally controlled in hard rock exhibiting jointing. And as mentioned previously, RocSlope can model real 3D slope geometries. At the bench scale, we are looking for potential crest failures. At the interramp scale, we are looking for possible crest failures and also where those are actually affecting the benches. And of course, there's always that potential to form deeper interramp failures. At the open pit or global scale, RocSlope can be seen as more of a risk assessment and hazard mapping tool to detect sectors which are prone to failure. RocSlope employs 3D limit equilibrium in its computation of block stability to obtain a factor of safety for each block. And as can be seen here, multiple blocks can be formed on any given slope. A bit more about the slope geometry. Rock slope geometry can contain multiple material regions, each with a defined unit weight and groundwater condition. The geometry itself can be created using imported 3D volumes, surfaces, or even point cloud data. And this can come from 3D mapping or 3D design software. And most 3D file formats are supported by our software. Material layers and water surfaces can also be imported in the same way, or they can be interpolated using boreholes. The process is even easier if you're already starting from a Slide 3 or RS3 file. RocSlope can directly import Slide 3 or RS3 models, including their external geometry, material properties, groundwater, supports, and loads. And after that geometry is created, all that's really left to do is add joints before we can run the RocSlope compute. Now, how are the joints defined in RocSlope? The most critical part of the model creation process is the definition of the joints, since joints basically dictate if and how blocks form. In RocSlope, joints are modeled as planar surfaces defined by orientation, location, and size. We are also not limiting the user to just a couple of joints. In fact, we can model hundreds or even thousands of individual joint surfaces. Since the mode of failure is structurally controlled, we are concerned with the shear strength of the joint surfaces themselves and not the intact rock mass strength. We can define any number of joint properties and choose from a variety of shear strength models, set waviness angle to account for undulations, and apply water pressure inside the joints. We provide the user with 3 different methods of defining the geometry of the joints, depending on what information the user has. So the first method is measured joints. And as the name suggests, these joints are measured either through scanline, borehole, or photogrammetry, where for each joint, we know its orientation, location, and size exactly. Information that is typically difficult to obtain is the exact shape of the joint. So we just model it in RocSlope as a circular disk with a specified radius. The data itself is entered in this Excel-like interface that you see here, which can support things like formulas, dragging cells, copy and paste. We can also import this data directly from a CSV file. If you're dealing with orientation data, it is likely that you started from a DIPS file. And we also support the direct integration by importing the DIPS grid data. The second method is synthetic joint set. Here we know the orientation, size, and spacing distributions, but we don't know the exact locations of the joints. Again, we also assume that these are circular disks. To obtain a single realization of the joint set, the orientations, sizes, and spacings can be sampled along the specified traversal path. The traverse could represent something like a scan line or a borehole. The orientation distribution can be directly imported from DIPS joint set statistics to provide a mean dip direction, and Fisher K value. We can also toggle different realizations for any given joint set. The third method is taking a surface or collection of surfaces and setting it as a joint surface. Now that can be any surface that's imported from a 3D file format. And these can include simulated jointing structures such as DFNs or real discrete surfaces which have been mapped out. A bit more about how joints are defined in RocSlope versus something like S-Wedge. So a simple limit equilibrium program like S-Wedge is a fast and easy to use tool for bench design. Not much information is required to define the joints, pretty much only dip and dip direction. And in an S-Wedge analysis, the joints are assumed to be ubiquitous and infinite, meaning that the joints can occur anywhere to form a block on the slope. This is of course a very conservative approach. Today, we have better technologies to be able to map out the structures, whether it be through LiDAR, boreholes, or photogrammetry, and this allows us to create models which are more realistic, using actual locations and known extents of the structures. RocSlope, in contrast, uses discrete joints, which are spatially referenced and finite. In RocSlope, blocks can only form where joints occur, persist enough to intersect, and daylight. So why does location really matter? From a risk assessment perspective, we want to know where failures occur. This might include questions like what region of the pit or the slope is susceptible to failure? What are the scales of failures in these regions? Is it a crest or interramp failure? This will help to answer if it's a bench face angle issue or an interramp angle issue. What causes these failures to occur? This might include having some understanding of the failure geometry. So is it planar, wedge, or blocky? What external forces are driving the failure? For example, water pressure and loading can drastically decrease the factor of safety compared to the dry and unloaded cases. Is the detachment of key blocks leading to some sort of large-scale global failure? After identifying the high-risk areas, how do we ensure slope stability and mitigate the risks? In support design, we want to identify locations and magnitudes of support demand and implement the appropriate support systems. Specifically, we want to identify and stabilize the key blocks. If we stabilize the key blocks, we stabilize the entire slope. RocSlope can help to answer all of these questions. Now I'm just going to pause to see if there are any questions. Ali Reza, can you please help me with seeing if there's any questions from the audience?
Sure. Thank you very much, Angela. There are a couple of questions here. One of them that is actually very interesting is, how is RocSlope different from S-Wedge? And can I replace S-Wedge with RocSlope?
That's a great question. Thank you, Ali Reza. So RocSlope was not really designed with the intention to replace S-Wedge, but rather bridge the gap between the features in S-Wedge and the need to create more complex and larger models. The most obvious thing that you'll probably notice between the two programs is the difference in modeling complexity. So for anyone who's used to S-Wedge or rock plane modeling, you'll notice how simple and fast it is. Basically, with a handful of inputs, the model can be computed practically instantaneously. And of course, if you do need to model something more complex with 3D models, that's where RocSlope comes in. Secondly, S-Wedge is really meant as a bench analysis software used for optimizing bench width and bench face angle. It takes into account the spill width and likely backbreak distances of thousands of realizations of wedges on the crest. And RocSlope is meant for more of a pit scale analysis, which may include both crest and interramp failures. And understanding the location and the scale of the failures is a big part of really what makes RocSlope a risk assessment software. And just so we don't slow down too much, I'm going to proceed, and I will stop again in a few minutes to see if any questions are there. And again, as a reminder, please feel free to type in your questions, and that way I'll be able to have Ali Reza read them out to me and I'll answer them. And if I can't get to them in the middle of the presentation, I'll try to get to them in the remaining 15 minutes at the end. Thank you very much. So now let's talk about the blocks. With many joints and joint intersections, we can form complex block geometries with any number of planar joint faces. For daylighting blocks, these will also have free faces, so basically what is exposed to the outside slope. The factor of safety for each block is computed by considering the block weight as the driving force and the joint shear strength as the resisting force. We can also model the effects of external loading by applying point, line, or area loads, seismic loading, and water pressure. Supports can be added to stabilize blocks in any combination of rock bolts, support pressure, and shotcrete. Now in RocSlope, we can perform a probabilistic analysis by assigning statistics to material unit weight, shear strength parameters, and water pressure. And from the analysis results, we can produce statistical plots like histograms, cumulative, and scatter plots for any selection of blocks. So it can be for a single block or for all failed blocks or any filtered set of blocks. And similar to a deterministic analysis, we can also view these in a heat map by contouring by the selected data type. So in a probabilistic analysis, we also have something in addition that we compute the probability of failure for each block. So in a deterministic, again, we're only looking at factor of safety, and in probabilistic, we get a factor of safety from the ratio of failed to sampled blocks. And in a probabilistic analysis, because you're looking at thousands of sample runs, we only report for these critical parameters like factor of safety, weight, required support pressure, and failure depth, the extremes, so the minimums and the maximums. Now let's dive a little bit deeper into how the blocks are actually formed. In any analysis, the most obvious place to look for blocks is anywhere where the joints daylight on the slope. In RocSlope, the joint traces can be shown where the joints daylight and intersect on the slope surface. So this should already be a fairly good indication before running any kind of computation, which regions may actually end up forming blocks. Now, a block which daylights is either stable or it's unstable. An unstable block is essentially a block with a factor of safety less than the user specified design factor of safety. And the first thing that controls the block's stability is the joint geometry. So if we look at the two orange blocks, we can see that the top one tapers out and can physically be pulled out of the socket. We call that a removable block. Now, in contrast, the one on the bottom is not removable. Blocks which are not removable are indefinitely stable, and this is regardless of the forces acting on it. Now, if a block is deemed removable, then the forces acting on the block will determine its factor of safety. All removable blocks will have at least one possible sliding direction in order to remove it from its socket. Now, a block can fail either by falling or lifting. So in other words, it has lost contact with all of its joints. Second way is by sliding on a single joint, or it can also slide on multiple joints. And this would occur along the line of intersection between any two joints. Now in RocSlope, we can also animate this sort of translation that you see here for any of the removable blocks in its computed sliding direction. To understand really the true extent of RocSlope failure, we have to also consider the blocks which are beyond the immediately removable and daylighting blocks. So the key block is the block of rock that, if it were to fail, would potentially cause the rest of the slope to fail. And as key blocks fail and get removed, adjacent blocks potentially beside and behind, which were previously stable, may now fail, leading to the successive unraveling of the slope. Now, looking at the figure on the right, RocSlope detects that the green block at the bottom, so basically at the toe, this one will fail first, followed by the purple block. So essentially that green block controls the stability of the purple block. Here's an example with a much more complex model and now looking at hundreds of blocks. So in a RocSlope successive failure analysis, we can identify the key blocks. These are the blocks that are failing in the first iteration. Now, theoretically, if these key blocks can be stabilized, then the slope would be stabilized. We can see the effects of detaching key blocks and how it affects the stability of adjacent blocks. If we continue to detach the failed blocks, we'll reach a point until only stable blocks remain. If we were to design a rock bolt system to stabilize the key blocks, we would need to know the locations of the key blocks and also the total failure depth, so that we pick a bolt length long enough to anchor into the competent rock behind. In RocSlope, the total failure depth includes the depth of the unstable daylighting block that you see on the surface and any unstable non-daylighting blocks due to successive failure. And this can be contoured directly on the slope. After the failed blocks are identified and computed, we can optionally export any of the failed blocks or the socketed slope geometries to pretty much any general 3D geometry format. As you've seen in the past couple of slides, in a typical model, we're probably not dealing with a single block. In reality, hundreds or thousands of blocks can be formed anywhere in the open pit. So for risk detection, we are not necessarily concerned about the minimum factor of safety for the entire pit, but rather where on the pit the lowest factors of safety occur. So as you see in the image here, we can create a heat map of factor of safety to identify the areas with highest failure risk. We can also contour by other parameters like the block weight to get an idea about the scale of failures too. For areas which are not meeting our design factor of safety, we can identify the support requirements. So where do we actually need to apply those additional supports, and what is the support capacity required? We can answer that by contouring by required support pressure, which is automatically computed by RocSlope. And this is to get an idea about the average bolt capacity and pattern spacing, which would be required. And what is the length of bolts required? So again, we can contour by failure depth to get an idea about the minimum bolt length to anchor into competent rock. Beyond the graphical representations of the block data, RocSlope also offers detailed block information for each block. And this includes information about the block's geometric removability, factor of safety, weight, volume, driving and resisting forces, sliding direction, failure mode, required support pressure, failure depth, and slope face area. And all this data can be exported to a CSV format. If you don't want to see all of the blocks which are computed, we can filter the visibility of blocks using advanced conditional statements on any block data type. We also have options to quickly toggle by result set. And the three options we have are looking at all valid blocks. But again, if you don't want to see all of the valid blocks, we can look at just the ones that are removable, or even all the ones that are removable and have failed. So in other words, they have a factor of safety less than our design factor of safety. If you require even more details for a selected block, we can also see the block in isolation and gather information about the joints that make up the block, the joint intersections, and block vertices. This, again, like the previous view, can also be exported to a CSV format. For large models, the pit extents could be several kilometers and discontinuities could be everywhere in your model. So this, of course, can be very computationally intensive. And ultimately, as the user, you may not actually want to compute all of it and visualize it. So similar to slide 3, we also have the option to apply search limits. And this is to specify inclusion and exclusion zones where blocks are getting computed. These search limits are volumetric regions, and multiple can be defined for any given model. So as you see in this image here, we also have this cool feature called auto search limits. And this will automatically generate these inclusion boxes based on the clustering of your joints. Now, one of the biggest challenges of working in 3D and trying to look at thousands of blocks is how we visualize them. In RocSlope, we provide different ways to visualize blocks, either by material colors, which colors the blocks according to the material colors, joint colors, which colors the blocks according to the joint property colors, random colors, which you see here. This one colors adjacent blocks differently to easily distinguish between the blocks. And lastly, active contour, which you've seen over and over for the various different data types being contoured. And this is, again, based on your selected data type. So these can be factor of safety, required support pressure, weight, etc. I'll stop again for questions. And Alireza, would you mind helping me out with?
This question actually has been repeated a couple of times here in the list. The main idea is that how is RocSlope different from slide 3 now?
Okay. So I'll tell you how they're similar first. So both programs deal with slope stability and both employ limit equilibrium. But the main difference is that RocSlope was created specifically for analyzing structurally controlled failures. So instead of sort of this searching for the failure surface like you do in slide 3, these surfaces are technically already strictly defined as the joint surfaces themselves in RocSlope. So in other words, the joints themselves control the formation of the blocks, which could or could not fail. And then these blocks are then treated as a rigid body in the limit equilibrium computation, where basically the resistance to sliding is provided along any of the sliding joints and the shear strength applied there. And of course, the driving force is self-weight. And RocSlope also allows for specialized input of the joint geometry and properties. And really a collection of hundreds or thousands of structures can be modeled. So we're not talking about, a handful of weak layers or anisotropic surfaces. We're talking a lot of fractures and major and minor structures. And even if you look at RocSlope results, the block information, for example, will tell you very specific information about things like what joints form the block, which joints are the sliding joints. So I think it's pretty obvious that every part of the RocSlope software was designed with this in mind. Okay, I think again I'll just stick to just the one question, and then moving on. So now what I'm going to do is show you guys RocSlope in action with a real live demo of how it's like working in RocSlope. So what we see here is the east sector of an open pit with multiple benches. So the results here have already been computed. So we can see clearly, where the blocks are, and we know the metrics about each block. The joint traces are also shown by the black lines, indicating where the joints are daylighting on your slope geometry. And I'm going to be working sort of backwards here, and I'm going to start with the results interpretation first, and then I'll show you how to create this exact model from scratch. So starting from this model, let's click on the results node here. And if you notice here in the properties pane, the results set that we're currently looking at is for all of the valid blocks. And in this particular computation, we have 1,245 blocks being formed. And the current coloring is by random colors. So this again just helps the user to easily distinguish between any neighbor blocks so that we ensure that they are colored differently than their neighbors. And to really get a better visualization of blocks and its shape, let's increase the transparency of the slope so we can see what's happening behind. Now, if you look with me, you'll see that there are quite a few blocks being formed which do not daylight. Now, these non-daylighting blocks, even though you don't see them on the surface, they may also pose instability risks if key blocks detach, and then this sort of successive failure is allowed to happen. And in our current RocSlope analysis, we are accounting for those effects. So in RocSlope, we call this feature successive failure. And again, it just starts from key blocks, checking if these are stable, and then moving on deeper and to adjacent blocks from there. Now from here, let's create a factor of safety heat map. Let's go to the results flow, and we'll click on this option here, which is contour blocks, also available in the interpret menu. And we see from the legend to the right that we are contouring by factor of safety. Now the regions in red and orange mark the areas which have the lowest factor of safety. And in our model, they are occurring mostly in the top few benches. And in most cases, as you see here, we're looking at over 1,000 blocks. And this might be a little bit too much information to be looking at. Because again, going back to what I spoke to earlier, a block can really only fail if it's geometrically removable and has some valid direction in which it can be pulled out of the slope. So to quickly just toggle our results set, we can go to our properties pane from our results node again, and we'll just switch this to looking at just the removable blocks. So since a block can really only fail if it's removable, technically failed blocks are just a subset of all removable blocks. So now let's look at only the failed blocks. So again, going back to the drop down under the results set in the properties pane, we'll switch it now to failed blocks. And these blocks are essentially blocks with a computed factor of safety, which is less than our specified design factor of safety. And the design factor of safety I'm using in this model, in particular, I'm using 1.2. And of course, we can contour by other metrics to get a better idea about the scale of failure. So things like weight, for example. And again, we'll just select it from the dropdown, the failure depth, and also the slope face area. We can contour by required support pressure to identify the locations and the average capacities required to be able to meet our design factor of safety. So let's now contour by required support pressure, select that. So as I mentioned in my slides, this is just one way of interpreting the data, which is graphically in this sort of a heat map or block contouring, as we call it in this program. But of course, we can also look at the blocks in a lot more detail by looking at it through the block information, which basically provides us a listing of all of the blocks which we're looking at. So here it's the listing of all of the failed blocks. And as you'll see, even from the first few, they all have a factor of safety less than 1.2, hence they are the failed blocks. And you'll see here also, since we are performing a successive failure analysis, it also will report the failure iteration. So the larger this number, basically later on it occurs in the successive failure. And anything that has a failure iteration of 1, this is essentially our key blocks. We'll also get information for each of these blocks, including things like volume, weight, driving force, resisting force, failure mode, sliding direction, required support pressure, failure depth, and the slope face area. Now, aside from just looking at the information in this view also provides us with a very useful function, and that is essentially an ability to filter by any of these parameters. So any of these metrics that you see across here, these are all things that we can filter by. So just as an example, let's look at all of the blocks that fail in failure iteration 1. So if I hover over the header here, click on this little filter icon, I can quickly bring up this little pop-up and just select basically everything with a value of 1 in this column. And you'll see it quickly filters the results as well. This view is being updated. And now what this represents is basically just my collection of key blocks. So if we compare this with our entire extent of the failed region, we can see that the key blocks are actually a very small region compared to the global sort of failure that we see if we allow blocks to basically fail in succession. So that's why it's so important to run a successive failure analysis, because again, it's too easy to just look at the obvious daylighting blocks, the ones that we know are removable, the ones we know have a low factor of safety. But then what happens if we actually remove these and detach these from the slope? What other instabilities might occur as a result of that? And one other thing I want to bring your attention to is notice how small the volumes of some of these key blocks are. So it's obviously not realistic to try to design support systems for these. You will not be able to apply bolt through these very, very small blocks. And in fact, even in the 3D view, you can't even see these blocks. So we can even filter by, combinations of different filter criteria. So here for volume, for example, I'll do the same thing. Click on that filter icon. And under filter rules, I'll set it to, just as an example, let's make it so that we don't include anything that is smaller than or equal to 1 cubic meter. And again, you'll see those ones get filtered out. Now to clear the filter, very simple, just click on this X button here to clear all of the various filter criteria that we specified. And you can see a summary of it at the bottom of this pane. And now we're back to looking at all of the failed blocks. Now, to get a better understanding and visualization of the order of this successive failure, other than just looking at this failure iteration column here, this is another thing that we can contour by. So we can look at the failure iteration and note that, again, my key blocks can be easily identified because these are my yellow blocks. These are everything that failed in my first failure iteration. And then you'll see sort of the failure progressively expand from that key block. So looking at the cyan blocks, these fail after the yellow ones are removed, so the key blocks. And then from there, the magenta ones will fail, and then the red, and so on and so forth. If for any reason you need to see any block in isolation with even more information than what you're seeing in the block information, we can easily do that by clicking on it, right click, and looking at the detailed block information for that particular block. And that'll bring up this detailed block information pane. And as you see here, the geometry for this particular block, it's quite complex, and it's composed of 10 planar joint faces. And of those 10, 4 of them actually become free faces. So this degree of freedom basically opens up due to the unraveling or the detachment of its neighbors in the successive unraveling scheme. We can also see additional information like we know the failure mode is sliding, but specifically which joints is it sliding on. So in this case, we can identify that it's sliding on joints 4 and 5. And again, all of this information, whether it be in this detailed block information pane or in the block information listing, this can all be exported to a CSV file if you need to process it elsewhere. So now that I've shown you most of the basics and the results interpretation, let's actually try to now recreate this exact model from scratch. And hopefully I'll convince you how easy and fast it is to do so in RocSlope. Now, starting from a new file, as with any new project that you start, the first thing we'll want to do is configure the project settings. So select project settings from the toolbar here. The units, we'll just leave it as metric, stress as MPa. For the analysis, we'll set our design factor of safety to 1.2. And again, this will be design specific. I'm just using this as an example, and we'll leave the successive failure analysis turned on. So this again just means that we're not just taking into account the key blocks, which are removable and daylight and fail, but we also look at what happens after that. Now, in the RocSlope analysis, as I mentioned earlier in my presentation, we are capable of performing probabilistic analysis by setting properties as random variables. But in this case, just to keep things simple, this was a deterministic analysis. So we'll select OK to save our project settings. And in RocSlope, we do have material properties for the rock volume, and we also have joint properties. So these are essentially the two properties that we have to define for every model. Now, to define the material properties, select Materials, Define Materials. Excuse me. And in this, we can define the rock's unit weight. And we can keep the unit weight as 0.026 meganewtons per meter cubic. And we can rename this to rock. And again, just to keep this analysis simple, we won't be applying any sort of groundwater conditions. Select OK. And for our joint properties, select joints, define joint properties. And in this dialog, we can define the shear strength and the water parameters for each of these joint properties, and then later assign those to the joints themselves. So for this model, we'll create two different joint properties, one to model the major structures and one to model the more weathered minor structures. So here I'll name my first one fault for my major structures. The strength type, we'll leave it as more Coulomb. And for the strength here, it's going to be a cohesionless shear strength with a friction angle of, let's say, 30 degrees. And here is where we can specify any sort of water pressure conditions acting in this joint. And in our case, again, we will just keep it as dry, so no water pressure effects whatsoever. And then we'll do our second one in the same fashion. We'll name this one weathered fracture. And again, we'll set it so that we're not using any sort of water pressure. So we'll set the water pressure method to dry. And for the strength, it'll be, again, a more Coulomb model, no cohesion, and a friction angle a bit lesser than the other one, so 25 degrees. And we'll select OK to save our properties. Now onto the slope geometry. The sort of likely workflow that we see is direct import from an existing sort of pit shell geometry or geometry exported from elsewhere. So for this model, this is exactly what I'm going to do. I'm going to import that sector pit shell geometry. So I'm going to go to File, Import Geometry. I'm going to select my open pit sector geometry. So here we see a preview of it. We're going to select all of the geometry and select Done to import it. Now, in order for RocSlope to recognize this 3D volume as the slope itself, we have to select it and go to Geometry menu and set that thing as an external. And you'll also note that for this particular model, again, just to keep things simple, this is a single volume, single material, and we have our previously defined rock material property set to this material volume. So now that we've done all of that, really the only remaining thing is to now define the joints. So the first thing I'm going to do is I'm going to specify my major structures. And these I actually have as a separate 3D geometry file, which mark where my faults are. So the import process is identical to how we imported this slope geometry. So again, I'll go to File, Import Geometry, and I'm going to select my faults geometry file. And here you'll see two major structures here, and select all geometry again, and Done to import. So these are just general geometry pieces to the model, but in order for RocSlope to know that we want to model these as joints, we need to select these, go to the Joints menu, and Add Joint Surface. And the joint property I'm going to apply to it is fault. So this just tells RocSlope that these are now joint surfaces. For my minor structures, these will be coming from a DIPS file. So what my DIPS file looks like is something like this. So this is coming from borehole and oriented core data. And from this DIPS file, we can directly import all 48 separate measurements, including the dip direction, and the location and the persistence values. So one thing that we can do in DIPS is, for example, like in the case of an oriented core, is we can take that data and process alpha beta angles into real dip and dip direction. So the alpha beta angles don't mean anything to us, and this is where sort of DIPS comes in. And of course, DIPS has a bunch of other functionalities that I won't dive into. Now let's take this and try to import it into RocSlope. So in RocSlope, in order to import that, that grid data from dips, we'll import it as a measured set of joints. So go into the joints menu again, define measured joints. Click on import dips button, and we'll select that file, that dips file that we were just looking at. The planes to import will be importing the grid data. And on OK, you should see all 48 joint measurements getting imported. Now, the only thing left to do here is to assign a joint property to each of these measurements. To select a joint property, double click on the cell and you'll see a drop down button here. And here we see a listing of our previously defined joint properties. So we'll set all of these to weathered fracture. And to quickly assign this property to all of the joints, because in many cases, we're not just dealing with a couple, it could be hundreds or thousands. We provide a very easy way to do that by right-clicking, assign joint property to all, and we'll do that with the weathered fracture. Select OK, and the joints get added to your model. And that's all there is really to the model creation process. And now all that's left to do is to compute. The first stage of compute is compute blocks. So this is where the engine will look at where your joints are intersecting with each other and also the slope volume. And it'll try to create closed volumes, which are essentially your blocks. So going back to my previous comments about why this is really a structurally controlled type of failure is that how and where your blocks form, it is strictly dictated by essentially how your joints are being input into the program. So persistence, orientation, location, all these kinds of things, they all play a role. We'll just give it a couple of seconds to finish. Now that our blocks are computed, we see basically all the blocks getting colored by random colors, and these are all of our valid blocks. The second stage is to compute the kinematics. Now this is where the engine will determine which blocks are removable and the appropriate factors of safety, taking into account all of the forces acting on the block. And now we're looking at all of the removable blocks. So after the kinematic compute, by default, we look at removable blocks because again, all valid blocks is not super useful to us since really only the geometrically removable ones are of concern. And really that's all there is to it. So I'm gonna go back to my slides now. Now, does anyone have any questions? And this is pretty much nearing the end of my presentation and all I have to say. So at this point, I'm going to open up the floor. And please, again, Ali Reza, could you assist in reading out the questions to me?
Sure, Angela. The list of questions is rather extensive. So I would promise here to all the audience that we will address all the questions. If not here, via email, we will contact you. I have selected a bunch of them. I will read it to you and I leave the answers to you. So one of them is that what type of surfaces can I use to model joints?
So in RocSlope, any single planar surface or even a collection of multiple planar surfaces, these can all be imported as a general geometry object and then set to a joint surface like the one that like what I showed in my demonstration. And these are not technically even restricted to surfaces which are completely planar. You can have technically curved surfaces too, but internally in RocSlope, what it does is it breaks down that surface into multiple planar facets and it treats each of these as a separate joint in the analysis.
Okay, thank you. About integration between RocSlope and rockfall tree. So if you have done an analysis in RocSlope and you know where the rocks are falling, where you have instability, how can I analyze it in rockfall tree and get the rockfall analysis hazard on that?
So it's not currently possible in this first release, but we are definitely looking into it for future implementation and in future releases, where we are going to introduce more of this integration. So where we sort of see this is again, exactly. So knowing where your failures initiate from, and also having an idea about the scale. So basically the size or the weight of these blocks, we can create some sort of statistical distribution even of things like location, size, and all this kind of information can then be directly imported into something like RocSlope to set the seeder locations.
Thank you. There's another one that is actually very interesting as well. How can we consider the strengths of the rock itself and include the bridging between the rock and the beach plains so that we can run a more comprehensive analysis?
So again, in first iteration, we decided to just keep things simple and just look at the joint shear strength. So you won't be seeing any sort of method of inputting rock mass strength into the model currently. But we are, again, going to look into it for future implementation, the idea of things like persistence, sensitivity, and rock mass bridging. So basically, what remaining area of intact rock mass would we have to shear through in order for this thing to, in order for this block to daylight and to be able to slide out?
Thank you. I guess one last one. How can we consider different realizations of DFNs?
So currently, again, this is not in first iteration, but if you want to do that right now, it'd be a manual process of importing your various DFN models generated from elsewhere. Again, we leave the importing very flexible. Any collection of surfaces, so these are your DFNs basically, can be imported and you just run separate analysis with this. But in the future, we are looking to be able to produce different realizations of DFNs directly inside of RocSlope and automate that process of generating multiple realizations and getting a nice distribution when changing spatial and things like size of the joints and these kinds of inputs.
I think I will leave the rest of the question for the email response. This is actually good for now. Thank you.
Okay. Thank you very much, Alireza. And we are nearing the end. So I do have one more thing for you guys. And I do want to pull up a quick poll just to see, you know, get an idea about your feedback in terms of what you see as being important features to implement in RocSlope for the future. And of course, if there's anything that's not already listed, please feel free to reach out to our tech support or email me directly with any of your suggestions. We're more than happy to get more feedback in any form. So I'll just leave that poll open for another couple of minutes. Okay, since we are actually running towards the end of the session, I'm going to close the poll and just say my sort of final remarks. So thank you very much, everybody. And it was a pleasure speaking about RocSlope today. And thank you for your time and your feedback. And just as a reminder, you can download a free trial of RocSlope on the Rocscience website or using the link here or in the chat.